The absolute CGS electrostatic unit of quantity. The absolute electrostatic unit of quantity is that quantity which would attract or repel a similar quantity 1 centimeter distant with a force of 1 dyne. From this as a basis, a full series of units of the ES system, as the term may be conveniently abbreviated, is deduced. Determination of the ES unit of potential. To obtain an experimental basis, we may start with the determination of potential difference. The attracted disk electrometer can be used for this determination. The attracted disk electrometer. It comprises a disk held above and parallel to a plate, the plate being much larger than the disk. The apparatus is so arranged that the attraction between plate and disk and the distance separating them can be determined. In the diagram, the disk is represented by the line S, the plate by the line T, and an annular plate surrounding the disk, as close to it as possible, is also indicated. By touching one of the two, disk or plate, with an excited conductor, a charge is imparted, and they attract each other. Call the surface density of the charge plus for one surface and minus for the other. The attraction of an indefinitely large plane with a surface density sigma for a point, in this case a unit of quantity, placed opposite its center is 2 pi sigma. This is the attraction of the plate for a unit of quantity of electricity on the disk. Surface density is the quantity of electricity per unit area of the plate or disk. Call the area of the disk capital S. Then the entire quantity on its surface is sigma times S. It will be seen that sigma represents the quantity on a unit area of the disk because the surface densities of the charges on plate and disk are identical. The attraction A between disk and plate is therefore A equals 2 pi sigma times sigma S, which equals 2 pi s sigma squared. This is equation 1. Because sigma s is numerically equal to the number of units of quantity on the disk, transposing equation 1 gives sigma squared equals A over 2 pi s. This is equation 2. If a point is situated between the disk and plate, both will act, one attracting and the other repelling any mass between them, and hence both exercising force in the same direction. The force at such a point will be the force exercised by one of the surfaces multiplied by 2. So 2 pi sigma times 2 equals 4 pi sigma. If a unit quantity is transferred from one plane to the other, as from disk to plate, the energy involved is numerically equal to the difference of potential between the two surfaces. This is because the product of potential difference by quantity is energy. And as the quantity transferred is supposed to be equal to unity, the potential difference and the energy have the same numerical value. Call the potential difference between the two surfaces capital P and the distance between the plates lowercase d. Then the potential difference will be equal to the force, 4 pi sigma, exercised on a unit of quantity multiplied by the distance of transfer d, giving P equal 4 pi sigma d. This is equation 3. Substituting for sigma from equation 2, we have P equals 4 pi d times the square root of A over 2 pi s, which simplifies to P equals d times the square root of 8 pi A over s. This is equation 4. The force of attraction A is measured. The area of the disk S and the distance d are known. Substituting for A, S, and d their values, the numerical value in electrostatic units of the potential difference between the plate and disk is found. In carrying out this calculation, CGS units must be used. The force of attraction must be expressed in dynes. Example, in an attracted disk electrometer, the area of the disk was 10 square centimeters. The distance from the disk to the plate was 0.5 centimeters. After imparting a charge to the disk, the attraction was 0.092 grams. Calculate the potential difference in electrostatic CGS units. Solution. Substituting for the symbols of the formula, that is, equation 4, their values, it becomes P equals 0.5 times the square root of 8 pi times the product of 0.092 times 981 divided by 10 equals 7.53 electrostatic units. The part of the expression in parentheses, 0.092 times 981, is the force of attraction in dynes, on the assumption that the force of gravity was measured by an acceleration of 981 centimeters per second squared. It is equal to 90.252 dynes. Other units of the electrostatic system. If one such unit of electromotive force were expended on maintaining a current of such strength that the two would expend 1 erg of energy per second, the current would be of 1 electrostatic absolute unit strength. The resistance of the conductor through which this current would be forced by a unit of potential difference would be 1 electrostatic unit in amount. From this basis, the whole series of electrostatic units can be deduced. The EM and ES systems of units. The value of a current or of potential difference may be determined in absolute units by various methods which give it directly. Examples of such are given in the preceding pages, where they are employed simply to give the concrete idea of what these units are, of how they are related to the three fundamental units of time, space, and mass, and of how they can be determined experimentally by direct use of the centimeter, gram, and second. One set of electric units is based on the attraction of oppositely charged surfaces for each other, or, what is the same thing, on the repulsion of similarly charged ones. This set of units is called the electrostatic series. Another series is based on the action of an electric current on a magnet pole. This series is known as the electromagnetic series. Both sets of units are CGS units and can be used for electric specification and calculation, one just as well as the other. The units of the two systems have values which differ from the values of corresponding units of the other system. The relation of the values has been determined by experiment, and the results are very accurate, yet not absolutely so. The EM absolute unit of quantity is equal to 3 times 10 to the 10th ES units. The coulomb is equal to 10 to the negative 1 EM absolute units, and therefore is equal to 3 times 10 to the 9th ES units. Exactly the same relations exist for the current units, so that the ampere is equal to 3 times 10 to the 9th ES units. The ES unit of potential is equal to 3 times 10 to the 10th EM absolute units. The volt is equal to 10 to the 8th EM absolute units, and therefore is equal to 1/3 times 10 to the negative 2nd ES unit. The ES unit of resistance is equal to 9 times 10 to the 20th EM absolute units. The ohm is equal to 10 to the 9th EM absolute units, and therefore is equal to 1/9 times 10 to the negative 11th ES unit. The EM absolute unit of capacity is equal to 9 times 10 to the 20th ES units. The practical unit of capacity, the farad, is equal to 10 to the negative 6th EM absolute units, and therefore is equal to 9 times 10 to the 11th ES units. The subject of capacity is treated of in Chapter 15.